Hello everyone, so welcome to the part 2 of this structural isomerism. Here we will discuss last portion of this structural isomerism, that is tautomerism. So here types of tautomerism, and then after deuterium exchange and all, and after that some examples we will discuss, and we will complete this topic completely. So let's start. First we will discuss definition of that tautomerism. So tautomerism in that oscillation of monovalent atom is called tautomerism. Either it will happen from 1 to 2 position, or 1 to 3 position, or 1 to 5 position, like that. So in that, two scientists were there. One was Frankland and one was Dupa. So both were that how it came into picture, that this tautomerism. So one was Frankland and one was Dupa. Both were doing experiment. They were trying to discover, they were trying to understand the structure of this molecule C6H10O3. C6H10O3. So Frankland, he discovered that this compound molecular formula in that two functional group is there. You can see here in that ketone and ester. When Dupa, he discovered that molecule structural formula, in that enol was there and along with that ester. When both scientists did that test of this functional group, so this compound was showing test of ketone, and along with that it was showing test of ester, as well as it was showing test of enol also. Similarly here it was showing test of enol, it was showing test of ester, along with that it was showing test of ketone also. So after doing this repeated experiment, then after they came to conclusion that this both molecules are in dynamic equilibrium, means here even though ketone is there, but due to equilibrium, enol also present. In that ester also there, ketone also there, along with that enol also there. So this both molecules exist in equilibrium, dynamic equilibrium. It is intra-convertible at room temperature. It cannot be separated. Since here you can see hydrogen is oscillating, is moving from 1 to 3. So hydrogen is moving from third position to 1, and double bond here. Here it is carbon double bond oxygen. Here it is carbon double bond carbon. Keto enol tautomerism. So since hydrogen is oscillating, so this tautomerism is also called prototropism. So this is introduction and understanding of tautomerism. Now we will discuss conditions of tautomerism. So condition is what? That A and B should have multiple bond, double or triple bond. B should be more electronegative than A, so that bond will get polarized like this. And along with that, alpha carbon should be sp3 and should have monovalent atom which will oscillate from third position to 1. So when this bond will polarize, so this H plus alpha hydrogen, acidic hydrogen, will migrate from here to, will oscillate from third carbon to this B, and it will form single bond BH, and here this A plus and this carbon minus will combine together and it will form double bond. This tautomerism in that acidic medium and basic medium both act as a catalyst. They increase the rate of tautomerism, or in auto-catalyzed mode also this reaction can happen. Clear? So moving further, now what is the difference between tautomerism and resonance? So difference between tautomerism and resonance is that in tautomerism, hydrogen atom is mobile. Hydrogen atom is oscillating from third position to first position. It is experimental. It is in equilibrium. And in that, keto is more stable than enol. Because keto is carbon double bond oxygen, its bond strength is more, so it is relatively more stable. Whereas enol, bond strength, carbon bond strength is relatively less, so energy is more, so its stability is less. Clear? Whereas coming to resonance, in resonance what will happen? that atom or nuclei position of atom is not changing. What is changing there? Double bond and delocalized lone pair always changing its position. It is hypothetical, means resonating structures are not actual structure. In that they are not in equilibrium, they are just separated by double-headed arrow. There is no effect of temperature and pressure on that resonating structure. And you can see that in two resonating structure, one resonating structure energy is less, means it is more contributing resonating structure, as compared to B, means its contribution in hybrid will be more. Now sometime what will happen, some compounds will having possibility to show more than one structural isomerism. What more than one structural isomerism? Like it can show ring chain isomerism, it can show tautomerism, it can show functional isomerism, metamerism, chain isomerism, position isomerism. Then how to give preference? Always remember RTFMCP, रात को FM चलाओ प्यार से, ring chain, then after tautomerism, then after functional isomerism, then metamerism, then chain, and then position isomerism. Means if any compound having possibility to show more than one isomerism, type of structural isomerism, this is the priority, that according to this only we will move on. Now types of tautomerism. So there are two types of tautomerism. One is here anisotropic tautomerism. Means here what will happen? Oscillation of anion, means anion will oscillate. Like here you can see this chlorine is getting oscillate, and means oscillating and is moving from here to this carbon. So this carbon, to maintain its tetravalency, this bond will polarize, and this oxygen negative will combine with this carbon plus. So oscillation of chlorine or oscillation of anion is anisotropic tautomerism. By the way, this is not in our syllabus. Just to complete that type, little bit we discuss. Now moving actually which we will study properly. So cationitropic tautomerism means oscillation of cation will happen. Means there are three types of actually cationitropic tautomerism. One is dyad system, then after triad system, and then after space tautomerism. So dyad system, only two tautomerisms are there, where cation will oscillate from dyad means 2, means it will oscillate from 1 to 2 or 2 to 1. Like here you can see cyanide. So in cyanide, hydrogen is oscillating from 1 to 2, means it will combine with nitrogen. So here formal charge +1 and here -1. Similarly, nitrite to nitro. In nitrite, hydrogen here it is connected to oxygen. It will move to nitrogen, 1, 2 oscillation. So these are only two types of dyad system is there. Next moving, which mainly we will study, triad system. Triad system means where hydrogen will oscillate, where hydrogen or that monovalent atom will oscillate from third position to first position. So cation oscillation between atom number 1 to 3 or 3 to 1. This is called triad system. For that already we condition discussed that A and B should be double bonded, means multiple bond. B should be more electronegative, and that alpha carbon should have monovalent atom, hydrogen, deuterium and tritium. It can occur in acidic medium also or basic medium also. So here you can see this is keto enol tautomerism. So since it is in dynamic equilibrium, so K equilibrium is equal to concentration of enol by concentration of keto. Since we know carbon double bond strength is more, so its bond energy is relatively less, means this molecule is more stable, means its percentage is more, and enol percentage is relatively less because its bond strength is less. Means carbon double bond strength is relatively less as compared to carbon double bond oxygen. Means here this is more stable, more percentage, here its percentage is less, so keto percentage is more, so K equilibrium will be less than 1. This is the one reason. that carbon double bond energy, bond strength is more as compared to carbon double bond carbon. Due to that, relatively it is more stable and this is relatively less stable. Another reason is that its pKa value is more. So since pKa value is more, so its acidic strength is less. Whereas here its pKa value is relatively less. So its acidic strength is more. So always the reaction will move from a strong acid to weak acid. Means in keto enol dynamic equilibrium it having more tendency to go backward. Hence K equilibrium will be less than 1. So both reason you should keep in your mind. First is that bond energy of keto is more than enol and keto pKa value is more than enol pKa. So its acidic strength is less, enol acidic strength is more. So reaction always moves from a strong acid to weak acid, unstable to stable. Clear? That's why K equilibrium will be less than 1. Since we discussed that keto enol tautomerism can be catalyzed by acidic medium also or by basic medium also. So if it is in acidic medium, then what will happen? This H plus will react with this lone pair, means oxygen electrophile and nucleophile. So here it will form OH plus, and this oxygen since having positive charge, so this bond will break, and same time this base acid H plus, so its conjugate base will abstract alpha hydrogen. As it will abstract alpha hydrogen, so here negative, so this negative will polarize this bond and overall we will get here phenol. Clear? So this like this happen in acidic medium, it get catalyzed and then after that reaction happen. Once again you try to understand here this H plus electrophile getting attached to this nucleophilic center, and since oxygen is having positive charge and same time this alpha hydrogen is acidic, so conjugate base will abstract this alpha hydrogen, it will form Hb, and here negative, so this negative will polarize and it will become aromatic phenol. Clear? Means phenol. Next, moving further, similarly you can see this compound is there. In this, again this is you can see here this is keto, here this is the alpha carbon, so sp3 carbon having alpha hydrogen. Similarly this is keto and it one also having alpha carbon having alpha hydrogen. In basic medium how it will happen? In basic medium it will abstract this alpha hydrogen which is acidic. So catalyst you know always will take in less in amount, very fractional amount. So it is 0.1 mole for this 1 mole. And due to that abstraction here it will be that carbon ion, and this electron will move from high electron density to low electron density. So this will be negative and here double bond, and then after from that water which here it came out, from that again it will take H plus and it will become OH. Now again this OH minus it will abstract again from here alpha hydrogen, and again it will be negative, so again from here polarization, so it will form enol and overall aromatic compound. So for each keto enol how many steps are happening? This is first step and second step again water, so 2 steps are happening. So for each one keto enol how many steps are? 2 steps. So here how many keto enol happen? One is here and one is here, so total 4 steps. Clear? Next, moving to third type of isomerism, tautomerism, that is a space tautomerism. It is also called para tautomerism. Whenever that at third position, if alpha carbon is not sp3, then we will go for fifth position. If at fifth position also alpha carbon is not sp3, then we will go to 7th position. If at 7 also not there, then we will check 9 and so forth. All odd position we will check. Hence it is called a space tautomerism. So tautomeric system other than diads and triads is called a space tautomerism. Here you can see 1, 2 and this is the third position, alpha carbon. Here it is, alpha carbon is not sp3, so condition is not fulfilled for tautomerism. Then we will go for fifth position. So at fifth position, here you can see alpha carbon means this is gamma carbon. This gamma carbon having hydrogen and it is sp3. Yes, so from here we will abstract this H plus and it will be negative through this resonating structure. So this negative will come here, and then after again from water that it will abstract H plus and it will become phenol. Means this is not keto enol tautomerism because this is not enol system, means this is not keto, this is, you can see, keto diene, like that. So yes, this is a space tautomerism, means when alpha carbon is not sp3, then we will migrate to fifth position, seventh position, and so forth. If that positions are sp3, so from there we will abstract H plus in basic medium, and that carbanion, according to that resonating structure, it will reach to high electron density to low electron density O minus, and again it will abstract from water H plus and it will become enol, means overall that tautomerism will occur. Now one thing you should keep in your mind, that gamma means fifth carbon hydrogen is more acidic than third carbon, means alpha carbon. Similarly, seventh carbon, if seventh carbon is sp3, so its hydrogen is more acidic than even fifth one and more acidic than first, that third position. How you can try to understand here? Simple, that this structure is given. So in this you can see that this one is alpha carbon, right, with respect to this functional group, whereas this one is, if here it is 1, here it is 2, so this is third, so third carbon is not sp3, so we'll go to fifth carbon. Fifth carbon having here, you can see, hydrogen. So this is gamma carbon, alpha, beta, gamma. So this is gamma carbon hydrogen. So alpha hydrogen, as we are abstracting from, let's suppose OD minus, so HOD came out and it became carbanion. So it having how many resonating structure? 1, and along with that 2. So it having 2 resonating structure. Whereas if we abstract hydrogen from here, so this carbanion having how many resonating structure? 1, then after 2, then after 3. So it having more resonating structure, means this carbanion is relatively more stable. So since this carbanion is relatively more stable, then if conjugate base is relatively more stable, means that hydrogen will easily furnished, means that gamma position is more acidic than alpha position. Understood? Means more than 3, fifth position, more than fifth, seventh position are acidic. So from there we will abstract alpha hydrogen, means that hydrogen, and then after through resonance again O minus will abstract from water H plus and it will do its tautomerism. Clear? So on behalf of this, one question I am asking to you, in keto enol tautomerism, is that alpha hydrogen presence is mandatory? Yes, it is mandatory. Because in keto enol tautomerism, alpha hydrogen must be there, then only that tautomerism will happen. But here, sir, you told that alpha hydrogen, if it is not there, then gamma hydrogen also. Yes, gamma hydrogen also should be there, means can do that space tautomerism. But here you can see that carefully, this is not keto, it is along with keto double bond also system is there. Similarly, here also you can see along with keto, here that double bond system, means it is diene keto system. So it is not keto. For keto enol tautomerism, always alpha hydrogen must be sp3 and must have alpha hydrogen. Then only that keto enol tautomerism will happen. So that is must and should condition. Next, after that, discussing kinetic isotopic exchange or deuterium exchange. So kinetic isotopic exchange or deuterium exchange, in that we will take base OD minus in presence of D2O solvent. And for prolong, if we'll keep, then all alpha hydrogen, if alpha hydrogen is not there, then S-base tautomerism. Through that also, all hydrogen will be replaced by deuterium, because that carbon hydrogen bond and carbon deuterium bond is more stable. So since more stable, so bond energy will release. So this compound is relatively more stable, hence it is favorable for deuterium exchange. Means here all hydrogen will be exchanged by deuterium. Here all alpha hydrogen will be exchanged by deuterium, because this carbon is sp3. So for one exchange, how many steps are there? How many steps required? 2. So here how many required? 6. And here 6. So total how many steps? 12 steps. Similarly, you can see this examples. Sir, how happened that mechanism? At last, I will tell its mechanism, so it will be 100% clear. Like here, you can see this is keto, so it's here this alpha position. This one also alpha position. For this keto, this is alpha position, right? So everywhere that all hydrogen will be exchanged by deuterium. Similarly, here you can see here this alpha carbon is sp2, so we'll go to S-base tautomerism. So here also deuterium exchange will happen. Here also one hydrogen will exchange into deuterium. Here also one hydrogen will exchange into deuterium. Sir, here tautomerism not happen. How it will happen? Yes, we will discuss. Don't worry. But remember, once if negative charge came in S-base tautomerism, from there we can take negative charge here also, and we can exchange hydrogen into deuterium. We will discuss in detail, don't worry. Means here that negative means here both hydrogen change into deuterium, exchange with hydrogen exchange with deuterium. Here also one hydrogen is there. Here also one hydrogen is there, that also exchange with deuterium. Here you can see, since that alpha carbon is not sp3, and that gamma carbon is sp3 but not having hydrogen. So if hydrogen is not there, means here first that carbanion will be not formed, means from here tautomerism will not initiate, means here no tautomerism at all. Similarly, here this is sp2, so here also alpha carbon condition is not fulfilled. Yes, this alpha carbon is sp3, so here all hydrogen will exchange deuterium. Clear? Now you try to understand how here it happened. That even here this is sp2, but here also hydrogen exchange into deuterium. Try to understand through one example and mechanism. Like here, this example, so here you can see this one is already hydrogen, so here the carbon only not there. This one you can see this carbon is alpha carbon, but this carbon is not sp3. So we'll go to fifth position is alpha carbon, gamma carbon, and it is sp3. So first what we will do, we will abstract alpha, that gamma hydrogen, since it is more acidic, so conjugate base will abstract and it will become carbanion, and this negative electron density will move from high to low like this. Here oxygen is polarized like this, means electron will move from high to low. So as it is moving, so its one resonating structure will be this, right? And from there this DOD which we took, because it is present in like here it is also not OH minus, it is also OD minus in presence of DOD, means solvent is DOD, so here it is OD minus. So OD minus abstracting this gamma hydrogen and it became DOD, correct? So this DOD is giving its one deuterium, where at alpha position. Is that clear? Now it having one deuterium and one hydrogen. Again OD minus will abstract and it will become HOD, correct? And this negative again it will move from here to here, this resonating structure, And now here again DOD will give one deuterium. Now after that again OD minus will abstract another hydrogen. Then again DOD will give one deuterium. Again OD minus will abstract one hydrogen. Again DOD will give one deuterium. Means OD minus came out. Means OD minus is behaving as a catalyst. Means it is in basic medium, it is catalyzed. So you can see all that gamma hydrogen also exchange with deuterium. I discussed that carbon deuterium bond is more stable, that's why it is more favorable and deuterium exchange is happening. And here at alpha, even though it is sp2, deuterium exchange happen with the help of resonating structure. Is that clear? Means this negative is traveling at third position. Similarly, here also that negative first will travel to here, and here also hydrogen will exchange into deuterium, and then after one hydrogen another one is there, that will be negative. Again that negative will travel to here, and further here both hydrogen will exchange. Clear? Similarly at this place also. So this is all about deuterium exchange. Similarly you can see this example also, that phenol is there, and in presence of OD-D2O, first what will happen, this is acidic hydrogen, so phenol is also acid. So here it will be DOD, and this O minus will travel to ortho position also and para position. At ortho also one hydrogen and para also one hydrogen, all will exchange with deuterium. Clear? Now generally keto is more stable than enol, but there is specifically 3 cases where enol percentage is more than keto. First, when keto is becoming, that enol is becoming aromatic, then percentage of enol will be more than keto. So in first case, if enol is aromatic, so aromatic is more stable than non-aromatic, it is more stable. Means here K equilibrium will be greater than 1, percentage of enol will be greater than keto. Second is keto 1,3 dicarbonyl compound. Keto 1,3 dicarbonyl compound, either in aldehyde or ketone functional group. So here you can see in gaseous phase, if it is in aqueous phase, then this result is not valid. So in gaseous phase, even this one, all those whatever we are discussing, that this 3 special case where enol is more stable than keto, only in gaseous phase. In aqueous phase, this all those not valid. So here you can see that keto 1,3 dicarbonyl system with active hydrogen. Active hydrogen means here it should have active hydrogen. So that active hydrogen, what it will do, that enol tautomerism, means here enol will be formed, and due to hydrogen bonding it will having chelation, 6-membered chelation, and due to chelation it will be more stable. Due to hydrogen bonding it will be more stable. Hence almost enol will be 99.9%, means 100%. This reaction will move in forward direction. K equilibrium will be greater than 1. And third case, when 1,2 diketo, but it must be log, means it should be cyclic. 1,3 diketo we discuss. Now it is 1,2 dicyclic keto, means it should be cyclic. So in that what will happen? In that one, if we will do enol tautomerism. So let's suppose this system is doing enol. So again here chelation happen. How membered ring? 1, 2, 3, 4, 5. So 5-membered chelation, and it is also more stable, 99.9%. Hence enol is more than keto. So what are the 3 cases where enol is more stable in gaseous phase? One is if enol is becoming aromatic. Second, which one? When 1,3 diketo, in that hydrogen bonding happening, and due to chelation it is more stable. And third one, 1,2 diketo, cyclic diketo. So in that also enol is more than keto. Clear? Now we will understand how it happened and some several examples. Like here you can see this facts, very important. Everything we are covering, means all advanced question, Olympiad, everything you can solve, including NEET and all. So here you can see factors affecting percentage of phenol. Here just one skeletal form we are taking. If R1 alkyl group, R2 and R1. This is keto and its tautomerism you can see here enol. So in that here chelation happening 6 membered. This is what 1,3 diketo. So 1,3 diketo, in that a special case we are discussing when enol will be more in percentage and when enol will be more stable. First, if R1 size is big, if R1 size is big, so due to that R1 size, what will happen? This portion will come down and it will start rotating. Yes or no? Like if this size is big, so due to that, it will start oscillating around this single bond. So due to that, chelation will be not effective. If it is started rotating, so due to that, enol formation will be not effective and chelation also will be not effective. So if R2 size is more, steric crowding will increase and enol percentage will decrease. Means it will start rotating and overall enol will be not that effective. So not always 1,3 diketo, in that enol percentage will be more. No. If R2 size is more, then enol percentage will be less. Second, if R1 and R2 both if size is more, so due to that steric crowding, enol will be less stable. Due to steric crowding, that compound will be not stable, enol. Third, if R1 size is big and R2 is small, so due to that R1 size, if suppose its size is big and similarly here also its size is big, so due to that R1 and this R1 will have repulsion because of steric hindrance. So due to that as they will repel, so here chelation will be compressed, means chelation will be more effective. So only in one case that 1,3 diketo, in that enol percentage will be more in gaseous phase when R1 size is more, R2 size is small. Otherwise, if both size is more, R1 and R2, or R2 size is more, then even though it is 1,3 diketo, their enol percentage will be not more. Some examples we will discuss to validate this point. Next, moving further, if temperature we will increase, even though it is 1,3 diketo system, in that chelation will be not effective, chelation will break. So hence enol percentage will decrease. Third point, which I told, it is only valid in gaseous phase. If we'll keep in aqueous phase, so you can see in keto, 1,3 diketo, here you can see polarization is more. So more polarization, so its solvation means with water interaction is more. Whereas here in enol, only one polar part is there. So here interaction will be, water interaction is less. Understood? So since here it will be polarization more, so due to that polarization its solubility will be more. Its solubility will be more. Like here you can see, if it is solvent is water, if solvent is water, so in solvent water what will happen? It will dissolve in water. It will dissolve in, so due to that more polarization, more solvation, and in water it will become stable, means its enol percentage will be less. Its enol percentage will be less. Similarly, if solvent will be another liquid solution, so you can see enol percentage subsequently little bit increased. If it is N-hexane, little bit more increased. If it is in gaseous phase, then only that enol percentage is more, chelation will be effective. Otherwise, if solvent like polars and all, their enol percentage will be less. Next, moving further, now we will discuss some examples. It's very important. Like here you can see mono keto group. So mono keto group, this is the mono keto group. Analyzing percentage enol content and stability through that experimental data. Like here you can see, let's suppose its enthalpy of formation or its energy of this ketone system is X. So here this enol, keto to enol tautomerism, its enol energy is more because here its bond energy is relatively, that bond strength is relatively less. So as bond strength is relatively less, energy in molecule is more. How much energy is more? 50 kilojoule per mole energy is more. Like experimentally its enthalpy of formation is minus 1870 kilojoule per mole, but here you can see its enthalpy of formation is 8020 kilojoule per mole. Means how much extra energy it having? Extra 50 kilojoule per mole. Means since it having more energy and bond strength also less, so more energy, since bond formation happening, so energy released is less because bond strength is relatively less. Here bond strength is more, so energy released is more, so overall its stability is more. So here also you can see its energy is x, but here since energy, that bond strength is relatively, formation which happen is relatively weak, so energy release also is relatively less, so energy is relatively here more, so x plus 50. Clear? Due to that, here that keto is measured, its percentage will be 99.9%, enol will be less than 1%. Clear? So this is in mono keto group. Which one is more stable? Ketone, then enol. Similarly you can see in second example also, that here this ketone and in enol, ketone having x, so it will be x plus 50 kilojoule per mole. So overall direction of equilibrium will be backward, 99.9%, this one only 0.1% like that, this one. Similarly in cyclic ketone also you can see keto to enol, little bit just percentage of cyclic enol increases, but still it is negligible, because if here bond enthalpy, that energy, if it is having x, so this will be x plus 50. Understood? So since it is having less energy, more stable, so equilibrium will shift backward only, so its percentage is more, direction of equilibrium backward. Next, moving further, like here as we discussed, this is ketone system, here enol is formed. So if its energy is x, so this will be x plus 50, but since here aromatic, this benzene, so benzene resonance energy is minus 152. So overall as we will add, so it will be x minus 102 kilojoule per mole. So you can see now its energy is decreased due to resonance energy of benzene. That's why we discussed that when enol percentage is more, first case, when enol is becoming aromatic. Due to that aromatic, its resonance energy, now according to data you can see its energy is relatively less, and hence it is more stable, almost 99% enol and 1% keto. Means reaction will move in almost in forward direction. K equilibrium is greater than 1. Next, here also you can see, since in this also, like here alpha carbon and here alpha carbon, so both side tautomerism, so due to that this one, so here two times happen, that here let's suppose this ketone system and energy is x, but here due to that it will be here also tautomerism happen and here also tautomerism. So overall x plus 50 plus 50, 100 minus 152 resonance energy. So overall x minus 52 is still, this energy is less, means it is 99%, means reaction will move forward. Similarly here you can see this is again ketone system. So in ketone system its enthalpy of formation is x, right? So here it is x, and since here once enol, here once enol and here once enol, so due to that enol, how much energy increases overall? Here also that 50, here also 50 and here also 50, so total 150, and resonance energy is minus 152, so here x minus 2, so still it is in equilibrium, means that energy is almost equal. So it will exist in equilibrium, means it will also having some percentage. Let's suppose it is 30% or 40%. So this one is remaining 60%. So now can we say that here in all these 3, 4, 5 and 6, which one having more in all percentage? Here this one, because here it is plus 50 only. But here plus 50 extra came, and in third one again plus 50, means it is 150. Means we can say that where it is more? In first one as compared to second one, and in third 3 times that enol formation happen. So overall percentage of enol is relatively here less. Now coming to one special example after ketone, ester. So this is ester. So in ester you can see this ester is doing resonance high electron density to low electron density. So its resonance energy is minus 78 kilojoule. Due to that delocalization of electron from high electron to low electron, what will happen? Its energy will release. That energy is only called resonance energy. So let's suppose for this ester system, if it having energy enthalpy of formation is X. So since here we are doing enol, so for one enol it will be X plus 50, and here now its resonance is also that disturbed. Now you can see it will not do resonance. It cannot do resonance. Lone pair, single bond, single bond. So overall here energy was releasing how much? Minus 78, means how much energy increased? 78. Means overall you can see here energy increased, means its stability decreased. Means ester will not do. If ester having possibility of keto enol tautomerism, if it is doing, it is out of 1 million, one molecule will do like that tautomerism. Why? Because its energy is more, almost it is backward, it is next to impossible. Means can we say that enol percentage were relatively more? Monoketo as compared to ester. In keto also we compare this 3 structure, all this 4, 5 and 6. 4, 5 and 6 here. Like here it having 1 times enol, here 2 times enol, here 3 times enol. So here percentage of enol mole, here then after relatively, here relatively least. Now we are moving to diketo system, which having active methylene group. You can see this one only. Second condition 1,3 diketo system. So let's suppose again its energy is X. Once we are doing enol formation, so X plus 50, but due to that enol formation, now this hydrogen is doing hydrogen bonding with this. So due to that intramolecular hydrogen bonding also some energy will release, sort of bond formation happening. Similarly chelation also happening, 6 members, so it is becoming more stable. So due to that also some energy will release. And you can see it having extended conjugation, double, single, lone pair. So like that it having extended conjugation, due to that also resonance energy or conjugation energy will release. So overall by this 3 factor, overall here this energy will decrease. Even it is X plus 50, it will be less than this energy. Hence due to this reason only 1,3 diketo system, in that you can see R1 is bulky group, but R2 here hydrogen is small. Hence enol percentage is more. You can see 80% experimentally, and this one is 20%. Now if instead of this, if here phenyl is there, diketo, and it having active hydrogen, so now what will happen? Again same like that here, that enol tautomerism happen, again chelation happen, hydrogen bonding happen. So let's suppose its energy is X. So this will be due to enol X plus 50 minus intramolecular hydrogen bonding, 6 membered chelation, and resonance energy here more. You can see here also extended conjugation, along with that here also. So here due to that more extended conjugation, resonance energy is more. So overall this energy will be relatively very less, means almost enol percentage 100%. Now coming to some special cases where 1,3 diketo system will not show, means its percentage of enol will be relatively less. Like here you can see this is methyl group, this is bulky, all three are bulky groups. So due to that bulky group, here that its enol formation is relatively less due to steric crowding. It is unstable repulsion happening. So enol percentage is 40, 60 percentage keto. If here more bulky groups are there, then very steric repulsion, due to that too much repulsion, steric hindrance, this enol percentage at all not possible, even though it is 1,3 diketo system, even though it is in gaseous phase. Is that clear? Because we discuss if solvent will be water, polar enol. So since here both is here polar, that dipole system, so due to that here solvation will happen more, so it is relatively more stable in water as compared to this. So its enol transformation will not happen, means enol exchange will not happen. So from here can we conclude that diketo system, which one? Where R1 size is big, either it should be CH3 or phenyl. There what it is? Diketo system, enol percentage is more because it is X plus 50 minus hydrogen bonding minus 6 membered ring minus resonance energy. Due to that its energy is less than keto form. Understood? Means its enol percentage is more. Similarly coming to monoketo, it is X plus 50 only, but in ester it became disastrous. X plus 50 plus 78 its resonance energy, because its resonance got disturbed. So this is the priority of enol percentage. First in diketo, then after monoketo, then after ester. This all those are very good questions of advanced and Olympiads level. Now here you can say that this ketone, in this ketone also there and ester also there. So in this ketone, alpha hydrogen here or alpha hydrogen here, both are sp3. So if we'll do its enol, so like suppose here in this side we are doing, so this hydrogen is doing a hydrogen bonding with this one also. So due to that you can see chelation happens 6 membered, and this ester resonance energy is not hindered, still it is active. Means 1 keto to enol X plus 50 minus intramolecular hydrogen bonding, but resonance is not disturbed, so resonance energy will not minus. So overall, means resonance is still active, so will not minus. So overall it is relatively more stable, this ester, when ester is present with ketone. So once again we will update our that point to remember what, that first diketo system, in that X plus 50 minus this 3 factor, in keto ester X plus 50 minus intramolecular hydrogen bonding, not resonance energy, because resonance is still here, also resonance was happening and here also resonance, it is like simply a spectator. Next ketone, it is X plus 50 and then after ester, so percentage of enol this. After that we discuss already that 3 factor, that first one, that if enol is becoming aromatic, second is that 1,3 diketo system that we discuss here. If keto ester is coming relatively more, then after ketone and then after ester. Now one more last factor we discuss where enol percentage is more, 1,2 cyclic ketone system. So that also we'll see. Like here you can see, if this example is given, so here this is ketone, here it is ester, here it is 1,3 diketo, and here it is ketone ester. So which one will be first? Diketo means R, then after keto ester, then this, then after ketone, then after ester. Clear? Similarly you can see here that this, if we'll do tautomerism, alpha carbon is there, so here it is non-aromatic, is becoming anti-aromatic, so its percentage will be very less, not possible. If suppose here we are doing one's tautomerism, so it having all carbons are sp2 and it having 2 pi electron. So from non-aromatic to aromatic, so this will be 100% factor 1 which we discuss when enol percentage is more. Now here you can see this in famous book Peter Sky, this is given that explain why that if 1 comma 2 di-keto system is there and if it is not cyclic, why here that enol percentage is not more. Yes, when we will try to do enol, here what will happen, its enol will be not effective. Why? Because this oxygen and this oxygen having repulsion. So to minimize this repulsion, through conformers it will rotate. So now it is in NT, and even though now it will do its enol tautomerism. So here hydrogen bond, here OH will come, this OH cannot do hydrogen bonding with this, so chelation cannot happen. So hence it is not more stable enol when it is not cyclic. But when it is cyclic, now it cannot rotate. So when we will do its that keto enol, so in keto enol it can do chelation, and due to chelation, you know, we can write here x plus 50 minus hydrogen bonding minus chelation. So overall its energy is less, its energy is more. So its enol percentages means overall its energy is more and its energy is less due to chelation and hydrogen bonding, even though x plus 50, hence enol percentage is more than keto. Clear? Then after here this fusion type enol tautomerism, this is given in that famous book J March. So this one also you can see in this what happening that, so in this what happening that since here you can see alpha carbon is sp3, so bond angle is relatively less, so due to steric hindrance it is less stable. But as due to tautomerism, here you can see C double bond O, so due to tautomerism here it became sp2, so bond angle is 120, so relatively as angle increase, so steric hindrance on this system decreases, hence percentage of enol is more. So as bond angle increases here, steric hindrance decreases. Now after this we will start that second part of this, conformers. So in conformers we will discuss that when that molecules rotating around single bond or when ring its flange are flipping, so due to that also their position will change, that we will discuss in conformers. Thank you very much, we'll meet there.